Picture yourself inside a neuron at the moment it fires. There is no warning. Nothing announces itself. The space is narrow and crowded, filled with warm fluid, drifting proteins, and tangled scaffolding. A place where nothing is still and nothing is empty. Molecules brush past one another, they collide, separate, and collide again. As busy as a shopping mall right before Christmas, yet governed entirely by chemistry and charges. Around you, the membrane is thin and restless, a tiny boundary holding a quiet chemical imbalance that's been maintained for hours. A sea of sodium ions waits outside, while potassium lingers inside, a fragile difference stretched across a surface membrane only nanometers thick. This difference in charge caused by the different ions is not accidental. It is maintained, molecule by molecule, by sodium-potassium pumps spending ATP, restoring tension after every small leak, keeping the system in an unnatural equilibrium. At first, nothing seems to change. Then the balance begins to shift. Somewhere ahead, near the initial segment of the neuron, voltage-gated sodium channels open as a threshold is crossed and sodium pours inward, pulled by electrostatic forces that have existed in silence for so long. The membrane's voltage reverses, and the change carries forward along the neuron. Like a wave passing through a stretched rope. You watch it roll along the axon, each stretch of membrane opening up one after the other. Because this axon is wrapped in insulating myelin, the current does not move continuously but leaps between Ranvier nodes where the membrane is exposed, hopping from one stepping stone to the next, all the way up the neuron. As the ion channels open, we see an influx of charged particles. The voltage flips briefly, then sodium channels close. Behind the wave, potassium channels open, potassium flows outward, and the membrane begins its quiet return toward rest. The signal passes, and the neuron carries on. Sodium is pushed back out, potassium is brought back in, and energy is quietly spent restoring the balance for whatever comes next. Pumps resume their steady work, using ATP cleaning up the aftermath of the spike and resetting the system ready for the next one. And while voltage is being rebuilt, chemistry shifts in subtler ways. Calcium, kept in low numbers because it is such a powerful signal, briefly enters at the axon terminal when the wave arrives, and that small rise changes everything. Pockets filled with neurotransmitters, held near the edge of the cell like boats waiting to dock, are guided towards the membrane by snare proteins, and their contents spill into the synaptic cleft, a space barely 20 nanometers wide, so narrow it almost defies the idea of space, yet wide enough to hold every thought you have ever had. Neurotransmitters drift across by diffusion alone, glutamate or GABA or dopamine depending on the neuron, binding to receptors on the next cell. Some receptors respond immediately, AMPA receptors opening to let sodium in, nudging the next neuron closer to firing. Others, such as GABA-A receptors, allow chloride to flow, making the neuron less likely to fire and softening the overall response. And some receptors wait. NMDA receptors require two conditions at once, both a neurotransmitter and the right voltage, before opening to let calcium through, strengthening the connection for minutes, days, or longer. Transporters pull neurotransmitters back into the presynaptic cell or into surrounding astrocytes. Enzymes break down leftover or lingering proteins. No individual signal acts as a command. Each signal only makes future outcomes a little more or less likely. And together those small changes accumulate until a potential has been reached and something gives. The synapse resets. The neuron simply returns to its resting gradients, maintaining differences, absorbing noise, repeating the cycle without pause, one small event among billions that together make up your thoughts.